certainly very, very happy to be here to get again and take the last time I was here was actually 2009. And actually, in a way, what I'm talking about is the same subject matter that I was talking about here in 2009, when I was actually only at the beginning of launching an effort in the direction. But I'm very glad that today I can claim I have a lot of quite interesting results to show already. Well, that's my title. And of course, my key interest, of course, is fundamental physics. And in fact, the first couple of pages may be what I have shown already last time. This is what I always believe in, that when we want to think about quantum gravity, since Einstein taught us that gravity is about space-time structure, quantum gravity should be about some sort of dynamic of quantum space-time. Okay, so we need some notion of quantum space-time before we can really get to quantum gravity. That's the idea, and that's what I always believe in. That quantum geometry would be some sort of non-commutative geometry. So I have been making this statement for over decades, well, over a couple of decades almost probably, that I believe non-commutative geometry is to quantum gravity as non-Euclidean geometry is to classical gravity. Well, saying that is one thing, having a way to really tackle it, to formulate it, tackle it is totally another. And I should say even up to now, I cannot claim I exactly have something like that. But at least I think I'm close, okay? And well, my program, a major part of it kind of starts from a hunch in that I was a student in quantum mechanics, that when people talk about things like, we can't say the moon is there when we're not blocking. Well, all the strange thing with quantum mechanics, we learn from textbooks that a quantum particle cannot have a definite position, but to be more carefully, that statement should be saying a quantum particle cannot have a definite position in the Newtonian model of the space. The question then is, could we just need a better model for the physical space, then we can talk about a definite position for the object. And it's along this line that I was thinking that that kind of space should be some sort of non-commutative geometry. And very intuitively, the position observable would be the coordinate, exactly the coordinate variable. Of course, that's the theme of non-commutative geometry that nowadays people are somewhat familiar with, but I think there was a key missing concept there that keeps us from being able to really make it work. And that's the key notion of my talk today. So for me, this is a dream come true. At least so long as quantum mechanics is concerned, I think I more or less have the complete story pieced together. Now, why I put my title that way? Because I actually think I do have something interesting to say about non-commutative algebraic geometry and quantum information on the top. Well, algebraic geometry, one can say is the most important development in mathematics in the last century. The key theme about it is, of course, geometry and algebra used to be what the two kind of basic structure, basic things mathematicians are interested in. And since Cartesian geometry, of course, we have the idea of coordinate description of geometry, and therefore we can construct some algebra out of a geometry, like the algebra of functions, like say smooth functions. The key theme of algebraic geometry then is actually you can reverse the process. You can start with a completely abstract algebra and construct every single geometric concept out of it. Well, I'm not going to use that kind of very abstract mathematical language In fact, I'm not going to put it in a very easy and intuitive physical setting. Okay, so actually, the mathematician goes so far as to say that under some proper condition, there is actually a 1-1 correspondence between an algebra and a geometry. So in a way, a geometric space and a particular algebra is two sides of the same thing. Okay? Now, my way of looking at it as a physicist is simply enough. The only kind of algebra we care about is an observable algebra. What else? And an observable algebra, what is the correspondent geometry for that observable algebra? Here, of course, we should start with the commutative setting, and the answer is simple enough. Symplectic geometry, the phase space. Okay, so we have physics is about dynamic. We have a dynamical theory, say Newtonian mechanics. We have a phase space that is a symplectic geometry, and we have the functional algebra as algebra of functions, observable for that system. Now, the 1-1 correspondence is easy to appreciate. It's just two sides of the same picture. In fact, pretty soon we'll realize one can call it exactly what? The Heisenberg picture and the Schrödinger picture in the quantum mechanical language. Now, here we're sticking with the C number picture, the commutative case, of course, classical physics. But anyway, we have coordinate, we have the canonical coordinate, position, momentum coordinate as a basic observables. All the other observables can be seen essentially as some function of the basic observables. And now, this is a really simple but extremely important mathematical statement about that that works inside of the picture. So mathematicians actually define states on algebra as functional. What do you mean by functional? Is really in this statement of the so-called Belfin transform. So we can think about some observable fxp. The observable, of course, for example, it could be like what it could be, say, the energy observable of a certain dynamical system. Then the observable would have a fixed value once you fix a state. And that value, of course, in classical mechanics would be a real number. Okay? So the so-called Belfin transform is to look at it the other way around. So you want to look at it not as the function as the value on the state, but a map of the state. The map the function, the variable to that. So you want to take the state as a map that send each observable in the observable algebra to a number, its value. We can call it the evaluation map. Okay? So that's the functional. Because what is a functional? A functional is just a map from an algebra from anything to the set of real numbers. Okay? So that's actually very simple enough. Now, I have algebraic geometry in this page. Now I have information, but only classical information. There was a very interesting statement from the philosopher Quinn saying 2b is to be the value of an observable. I'm sorry, 2b is to be the value of a variable. Okay, so those observables are variables. The value is what we were really interested in. The value is what information is about. In fact, I would claim any information is like that. Any information has to be carried by some physical system, and it is encoded into what? The value of a certain variable for that system in the state. That's the only way to think about information in the physical way. Okay? Now, the last two lines here are extremely important. First thing is this very simple statement. I claim this is a lot more than a functional. It is an algebraic homomorphism. is a map from an algebra, the algebra observable, to another algebra, the algebra of real numbers. And as such, is a homomorphism, meaning what? The complete algebraic structure, say some algebraic relation among observables, would be completely preserved by the map. So whatever, if two observable, the product of two observables equal to a third observable, the product of their value for any state has to equal the value of that product observable. That is what you mean by this algebraic homomorphism. Okay?
But this doesn't hold in quantum mechanics.
That's what I'm going to tell you. It holds exactly when you know how to look at, or you can say construct that homomorphism. You can't do it with a functional. Because a functional, by definition, map an algebra to real number. And real number, of course, is a commutative algebra. In order to have an algebraic homomorphism for quantum mechanics, you actually, that's the next page, you actually need to what? You need to map the algebra to another non-commutative algebra. In order to have an algebraic homomorphism, you have to start with if you start with non-commutative algebra, of course you need the range to be a non-commutative algebra. So you need something more than a function. But the good thing is the state, a quantum state, not only fixes that functional for you, it actually gives you the whole homomorphism. That's the key point. And I'll show you the explicit mathematics in a while. Okay? So a quantum state can be seen as more than a functional. You can look at it as exactly such an algebraic homomorphism that now map the non-commutative algebra of observables to a non-commutative algebra of their values. Now you have to represent the values by some element of non-commutative algebra. That's what I call the non-commutative values. So that you preserve that homomorphism. And this non-commutative value as a value of some quantum observable, of course, is a piece of what? Quantum information. In fact, I would claim this is the most direct, the proper way to look at quantum information. Otherwise, we are still trying to describe quantum information in through some classical language. This is the direct quantum language. Okay? And we can go back up a little bit on that. Well, the two picture. We start with non-commutative algebra, quantum observable algebra. Of course, what else do we want? Symplectic geometry, do we have it? Yes. The quantum phase space, look at it. You want to look at it as project Hilbert space over here, or directly just as a Hilbert space. It is a symplectic manifold. It is a symplectic geometry. In fact, quantum mechanics is exactly that Hamiltonian dynamic, nothing more than that. And all that thing wrap up. So this last line, respond to what I just did here, following that question, is of course dynamics. The point is dynamic is just symplectic geometry. When you have symplectic geometry, what do you have? You have equation of performed like that. For any function on that symplectic geometry, or for some xs, some Hamiltonian function, this one, I mean Hamiltonian function in a mathematical sense, some generic Hamiltonian function. Those are just functions which generate a one parameter flow on the phase space that that draw lines of constant value for the hs. And with that kind of any Hamiltonian function, any other observable function will follow a differential equation like this. Now, what is the S? Well, S is the parameter, the single parameter transformation hs generate. The physical meaning of it, of course, different hs correspond to different S. If the hs is, say, the energy observable, or you can call it ht, because that parameter is exactly Newtonian time. But say you can pick hs to be angular momentum, In that case, your S would be the angle theta. We know the angular momentum generates rotation. So, so all those kind of structure are completely there, so long as you have the symplectic geometry. So I think the dynamic is already there in the geometry. Of course, the math cannot tell you which parameter is your Newtonian time and which Hamiltonian is ht. That part you have to rely on physics to determine. But otherwise, all those structure, all those equations are completely there in the symplectic geometry. And actually, my unique approach to the problem is exactly this. It's essentially all here. First of all, what kind of non-commutative geometry we interested in? Symplectic geometry. I'm not interested in anything that is not symplectic geometry because that has nothing to do with physics, because that has nothing to do with dynamics. Okay. Now, on that setting, you have the dynamic equations, like in the quantum case, you have exactly the same analog, and this quantum Poisson bracket is just essentially the commutator. In that case, what is this equation? It's exactly Heisenberg equation of motion. Okay, of course, usually we look at Heisenberg equation of motion only in terms of what? Time evolution. But again, it's the same structure there within, just on the symplectic geometry. The only missing key to piece everything together consistently is this notion of non-commutative value. Okay? Because I actually want this infinite dimensional discrete space or projective space, which we understood as an infinite dimensional real manifold, complex manifold. I really want to look at it as a non-commutative geometry with the position observable and momentum observable as coordinates, some sort of non-commutative coordinates. Okay. Now the next page is a little bit of elaboration on that notion of algebraic homomorphism. I guess I pretty much say that already. So you want the evaluation map to be an algebraic homomorphism so that it will preserve all the algebraic relation between the observable as variable and their value on any state. And this is extremely important for physics because when we have a statement that a certain observable, for example, the eddy is observable for certain dynamical system, it is given in terms of something like this, for example. How can we check it? There is no way to check the relation between the variable as variable. You check the relation by applying it to a definite state by looking at the relation between the values. If the relation between the variable doesn't respect the relation between the observables, how can you check it? That's a major part of the difficulty with the quantum mechanics. Well, you would say we successfully check quantum mechanics in many different ways. Yes, because we're actually pretty much going using that, something like that value, something like that non-commutative value. Only that is not exactly it. I'll help you. Say more about that in a while.
So in the previous one, in the classical case, phi
is a state, right? That evaluate or observable to give it a value. So if I have an observable E, which is equals to the observable P, this combination of observable P and X, then say for a particular state, if the X value is 2, the P value is 3, then the value of E has to follow exactly that relation.
So 2 and 3 is arbitrary you just given?
Yeah, I just give it as an example.
So the meaning is that the position of the particle is 2.
If the position is 2, the momentum is 3,
like
then that E has to be 3 times 3 plus 2 times 2. That's the whole point about the algebraic homomorphism. And of course, when you apply it, for example, to the XP thing in quantum mechanics, then, well, this is just the evaluation of what? The Heisenberg commutation relation, right? then it's clear that in order for this condition to be satisfied, this value of an observable like x here cannot be a real number. It has to be an element of some non-commutative number, where a non-commutative algebra.
Okay, so let me this way. So in the first page you described in terms of symplectic geometry, the classical system. Here, I guess this is the well-known classical system.
Yeah, this is completely well-known.
Okay. The next
except
page,
that people never emphasize is actually an algebraic homomorphism.
But in the next page, is also the same as the usual quantum mechanics.
The same can be done with the usual quantum mechanics, exactly the usual quantum mechanics.
But what bothers me is that the evaluate, so is the observable algebra A to up to
this evaluation map, this non-commutative value. I haven't defined it for you yet. Yes.
Because in the
I'm just telling you the picture. I haven't given you that exact definition, except when you describe non-commutative value. And of course, I have it in the coming pages.
Simple question. Do you need, for the non-commutative to a true number, do you need only H bar or you need something more?
H bar?
So H bar,
it's not about H bar.
H bar is the origin of the non-commutativity.
It's not about H bar. I don't need to worry about it. Whatever. So you give me some operator relation. I have this particular non-commutative value thing defined. I'll tell you how to get to the value of each of those operators and how to get that result.
So I thought if I send a Planck constant H bar to 0, then I thought everything is commutative and I'll arrive at the
yeah.
But here, is H bar the only origin of the non-commutativity, or do you need some more number like a Q number?
In that case, you're right. It's the only origin of non-commutativity. Yes.
And but since when you say Q number, you are introducing some other non-commutativity in the game. So maybe you will say later.
Yeah, I think so. Just to clarify where you are now. So usually in the classical picture, you may have the beta will be an operator. The state and the numbers you're talking about would be the expectation value of the operator on the state.
Exactly.
So what you're going to do is to change that recipe.
No, I'm going to extend it.
To extend that.
The expectation value number is a small part of the full value.
Okay, so you're going to.
I'll give you the full value.
We have to wait. Okay.
Well, I think it's right there. Actually, yes. It's exactly common.
This is map 5 can be just identity.
Map 5 is defined by a state. It's defined by a state. And for each state, the observable has a fixed value. So in that sense, it cannot be identity. It's a map between the algebra of variables, of values.
And it depends on state, you're saying.
Of course, because a different state would give a different map. Because a different state would assign different value to the same set of observables. But for any state, that map is an algebraic homomorphism.
But at the end of the day, do you have a C number physical measurable quantity or not?
There is some, I will show you a way to describe that non-commutative value in terms of real number or complex numbers. In fact, we should just go right to that.
So,
Let's just go right to that.
So are you considering the unitary algebra and the unit preservation? So are you considering the unitary algebra and the unit preservation?
I'm talking about the quantum observable algebra.
So I'm asking the unit preservation through the homomorphism. Identity map to identity elements.
You map the identity element to
the identity element in the Q.
Yes, exactly. Of course. In fact, you map a classical observable to a classical value. I'll even show you that. Okay, this is what it is. It's so straightforward. Okay, so this is the expectation value function, right? Everybody knows about it. So you have to just point out the functional will give you that value. The non-commutative value, a way to represent a non-commutative value is this infinite sequence. The first term is the value of the expectation value function. The later terms are what? Each this v beta n is this. So it's the coordinate derivative of the expectation value function. So you have to include the value of the expectation value function and the value of all its first coordinate derivatives. That gives you the complete set of values.
Coordinate of what? Space coordinate or what?
Cubic space. So the state, I pick an orthonormal base, any orthonormal base. I have a coordinate system on the Hilbert space. A state would be written like that, right? In terms of linear combination of the base states. So I have this coordinate, Cn, complex coordinate, that describes a state. So that's the differentiation. So of course, the exact v beta n depend on the choice of base. But this whole thing, well, I want to emphasize this non-commutative value is really an element in a non-commutative algebra, right? So, for example, you can think about a very simple non-commutative algebra, the algebra of three vectors, where I have the non-commutative product being the vector cross product. Of course, you can represent that element of the non-commutative algebra, that three vector, by its three components. But the component value depends on the choice of base. It's not unique, but it's the same vector. And that algebraic relation is independent of the base choice used to represent it. So this is really an element of the non-commutative algebra of values. But fixed base, you have particular way of writing it as an infinite sequence of complex numbers. Okay. Now, how this work is simple. I took it from this Italian gentleman. They have a paper in 1990. They don't have the notion of non-commutative value, but they introduced this very important thing, what he calls scalar product. So the thing is, for operator beta, we can, for each operator beta, we can define this expectation value function. And this is what? It's not completely like a classical observer, right? There's a function on the phase space with this complex number coordinates. And you can also put it in terms of real number coordinates. It essentially just a real and imaginary part of that complex number. Okay? Now, what they introduce is something called they call a scalar product, which is a product between, say I have an operator beta, I have another operator gamma. Then I have an F beta, I have an F gamma. What they introduce is a product, they call it scalar product, between F beta and F gamma that will give you exactly F beta gamma. Okay? So now every quantum observable we use to represent it as an operator on the Hilbert space now can be represented by a function on the phase space. Pretty much almost totally in the classical sense, except that you need a different product. You need a non-commutative product, which they give to you. And with the non-commutative product, you have this relation. This is F beta. F beta gamma. F beta gamma depends not only on F beta and F gamma, it depends also on their first derivatives. And this product, of course, is non-commutative. Okay? Now, what I have done is just, in that sense, a very simple thing. If I have a relation like that, then I can define this value so that I have therefore algebraic homomorphism. Because if this, I have relation all satisfied by that, I can have express F beta gamma in terms of F beta, F gamma, and the derivative of F beta and F gamma. I can express the derivative of F beta gamma in terms of, anyway, the information available there. these are the matrix elements. Yes. Then I have you have this Taylor product as relation between functions, and I'm just applying it as relation between the value of those functions. Only that it has to include the derivative functions.
What is the kappa in the star in the product? Kappa? Yes.
The product is defined. It's just a sum. It's just a notation for the product.
Scalar product.
Hmm?
Just scalar product.
They call it Taylor product.
What is V beta gamma n? The second equation, right?
So,
It's,
this is
see,
one
V
of it,
beta n
right?
is in the derivative case.
This is the derivative.
Okay. Now the second.
So this one is the derivative with respect to the complex conjugate C bar n.
No, V beta gamma n, the second equation. Where does yeah, no, the second.
But you mean this one?
Yeah, this one.
This is the Cn derivative of f beta gamma.
Okay.
Because I also need that to have the complete picture for the value, right?
So this star Taylor product is defined by the
It's defined by this equation, you can say.
left-hand side of the red equality.
Hmm?
The left-hand side, eta gamma, and then.
Yeah, it's defined by this equation. Yes.
But that comes from left-hand side of that equality, the Taylor product. Yeah, the red colored one.
But that comes from
The right-hand side is defined by the left-hand side, or the top
yeah,
one.
the product, this Taylor product is defined exactly by this.
But that comes from left-hand side.
I don't understand what you mean.
The left-hand side of that equality.
Yeah, that this part, the content of this part is this two function. Well, or the easiest way to understand. I mean, in fact, their paper present the whole thing in some very abstract differential geometric language. Which and it took us quite some time to work out a nice coordinate representation for it.
Is it commutative or non-commutative?
It's not commutative. Because
derivatives.
here, right? You can think about it. If I have f beta gamma, a gamma beta, I will have f gamma f beta here, which is the same. But here I will have derivative of f gamma with respect to Cn, but derivative of f beta with respect to Cn bar. So I will have the complex conjugate of this thing. This is a complex number. F beta gamma will equal to this plus the complex conjugate of this thing. And of course, and this actually, this is a simplified equation, I should clarify that. This is a simplified equation which works for beta gamma being both Hermitian. Otherwise, we need to write it in a more general form. And of course, you know that when beta gamma are Hermitian, f beta and f gamma are real functions. Real value function. But f beta gamma is not. Because the product of two Hermitian operator is generally not Hermitian.
But in your definition of V beta n, I thought it's always derivative with respect to z, not z bar.
This one has a bar in it.
So you change the
Oh,
order
this is
of
V
n
gamma
bar,
n bar.
but the order of n and bar remain the same, but beta and gamma change. That's the reason.
Okay. I didn't.
Yeah,
Yeah, there is a bar. Maybe it's somewhat difficult to
Okay.
okay.
Got it.
But above that, I mean, the red line, you wrote down eta gamma, yeah, inside bracket, beta gamma. So the red line.
Here.
Yeah. Is it defined?
Yeah. Beta gamma is an operator product. Beta and gamma are operators.
So it's closed. So that has this that left-hand side should have its own definition in terms of your phi definition. Yeah? Phi.
Yes, no problem. Actually, no problem.
And then you are saying they agree.
Yes.
So black line is kind of evaluation.
Yeah, that's
Of the
showing you the content of what you mean by the Taylor form. In the functional form, not in form of values, but of course you have the functional form, you have the value. Okay. So That's what I mean by that, right? This is the expectation value function. In fact, we're just completely using the expectation value function. But you have to go beyond just the real number value at a fixed point. Of course, the quantum theory predicts the whole function as a function of the variable coordinates. Then you also got the derivative, everything there is completely predicted by the field. There is another way to look at it, actually. This, if you think about it, it has something to do with Taylor series expansion. I have a function. I want to look at the local representation of the function. The value of the function at that point is one piece of information. More information can be encoded in what? In the derivatives. So you can do a local Taylor series expansion of it. Okay? But then this is actually a lot more amazing. You don't need the higher derivatives. You only need the first derivative. Well, I cheat a little bit. You actually also need the second derivative because these are the matrix elements, right? The matrix elements are exactly what is related to the second order derivative. Okay? But why don't I need higher order derivative? Well, that's the interesting thing. And there's some more tricky mathematics behind it. Because you take such an f beta as a Hamiltonian function, it actually generates this Italians, they call it this kind of Hamiltonian function Taylorian, because they generate Hamiltonian flow, which does not just preserve the symplectic structure, it also preserves the matrix. That's why they call it Taylorian. I mean, of course, think about Hilbert space or projective space. It's a Taylor manifold. It's a Taylor manifold. You have the symplectic structure, you have the Riemannian metric, and in fact, the two are essentially tied together. Okay? So, and with this property, one can show that this class of function actually they preserve also the Riemannian metric, so they are isometries. Okay? And because of this property, you can show that this is a restricted class of function instead of general any function on CNC and bar, which may not represent any operator in the Hilbert space language. So this restricted class of function has that property that you only have independent derivative up to the second order. All the higher order derivatives can be expressed in terms of the lower order derivatives. Now, the other thing is, actually, these two gentlemen in 2003 published a paper with exactly this title, substituting a qubit for an arbitrary number of classical bits. So if a real number is one piece of classical information, a piece of quantum information would contain a lot more than one real number. How many you have? Well, that depends on the dimension of the Hilbert space. So in the most general case, infinity. Okay, but that's how it works here. And even more amazingly, in fact, this is brand new. I hope about it. After I arrived in Korea, I actually had worked quite some time working on a paper because I just read this somewhat old paper in the year 2000 by this two gentlemen, Deutsch and Hagen, talking about locality of quantum information from Heisenberg picture. They're saying that even for an entangled state, of a composite system, there is a way to represent all the quantum information locally. And it's in terms of what? In terms of they face it as, that's why they call it from the Heisenberg picture, because they are looking at a particular situation of quantum information flow in some qubit system, and they face it in terms of some time evolved observable. But That's what I try to work on. You can get rid of those, in a sense, garbage. That the extra things that come from the particular time evolution, time quantum information full picture, and get it down to the very basic thing, which is essentially, they essentially give you a way to define some non-commutative value, but a more complicated way than the one I showed you here. Okay. But yes, being inspired by their argument, I can show very easily that the non-commutative values carry full information about a composite quantum system, even for entangled state, and all those information are locally stored. Not just locally stored. The non-commutative value of a local observable is independent of whatever you do to the other part of the system, even for an entangled system.
That seems to be quite interesting claim. So
well, it's actually extremely easy to show.
Right. I mean, what do you mean by locality? Locality usually so
that's what they mean by it.
Okay, then like you said, even the entanglement state, there's
yes.
some local.
Now let me put it this way, right? So the standard EPR case.
Yes.
I have two particles. The basic observables are the position and momentum of each observable. Now, for any state, I can take an entangled state. You use my definition here, you can expect the non-commutative value of the local basic observables, the position and momentum for particle 1 and particle 2 separately. You can write down their values. Now, the claim here is those values. First of all, there's a local information, right? Because this is about value of observable for particle 1 and value of observable for particle 2. So they're local information. Second, the value for the observable of particle 1 would not change if you do something to particle 2.
Sorry, everything depends on the state. The state is modified. If you do something to the state, it's the problem.
The state may be modified,
yeah.
But the value, when you do something for particle 2, the state for the composite system of course will change, right?
The status collapses. This is the problem.
I talk about it in that paper actually. The wave function collapses is more tricky, okay?
Yeah, of course, it's not clear. Nobody knows exactly what happens, but this is the picture.
If you look at it naively, it's not a local process. If you look at it naively, it's not a local process.
Yeah, of course.
But the locality statement is about you mix it up. You apply some local process to particle 2. That would not change the observable for particle 8.
But this
that condition is satisfied.
But in general, the expectation values change because it's the state changes, the expectation value change. But maybe what you're claiming is that this definition doesn't change. No, I don't know.
No. I'm saying when the state change, this function changed, right? But no. Actually, no, that's not true. The state phi is a state for the composite system.
Okay.
When you do something to particle 2, that's full state change.
Yeah, the state depends on the z. The z changing.
Yeah, one more. But the expectation value function for an observable of particle 1, for local observable of particle 1, that expectation value function doesn't change.
The value itself. So
the whole function doesn't change.
The function doesn't change.
The function doesn't change. That's why they don't expect
it's the same function of different z's. This is what you're saying. Because the state, state is determined by the z's. The state may change, but the state is a quantity of the state, right? That's the state. So it's the same function of different z's. Because the state is changing, right? You have a state phi that is a superposition of some in the base in n. Now you modify the state. The state, for instance, collapses in an eigenstate of n.
No. As I say,
all the z's
as I say, this doesn't apply to the so-called wave function collapse, as I talked about in the paper, because the wave function collapse if you look at it, you want to look at it naive like that within just the system, it's not a local process. I'm talking about local process. You do something for on particle 2, not touching particle 1 at all. The value for particle or observable of particle 1 itself, they don't change.
You have to digest.
Let me ask
Well, can talk about it more a bit later.
one more time, lastly, about this scalar product.
Yes. You
have a definition of F beta on the top equation, yeah? F beta is expectation value.
Yeah.
So there, if I replace beta by beta gamma,
Okay.
Yeah, you have the same expression, of course.
then do I get that equation?
Of course, this applies to every single operator.
So this is not a definition. This is really what you get. So it's you calculate that.
Yeah,
This is what you,
Yes, that's what
I calculate that based on the Taylor product definition this guy's OI.
but what is saying is that you can calculate instead of beta. You said you take gamma beta. It should be an operator. You can calculate everything.
Of course.
This
is a general expression for every single operator.
So that means that the left-hand side of the color product, beta gamma of phi, can be calculated without using the right-hand side by just redefining the operator. Instead of beta, you write a gamma beta.
You mean
here? No, left-hand side, the left-hand side. Here. Instead of beta, use gamma beta.
Of course. You have an F beta gamma like that.
Then it's harder to see that you get that.
This is the relation between
This is an identity.
Yes.
The line below is an identity.
Yes.
And so for some reason, these gentlemen call this color, it has a name, but because it seems that it is a definition, but it's not a definition.
It's a definition. It's a definition of that non-convergence product between F beta and F gamma.
Okay, you give a name.
Which serves as the
identity. It is an identity, of course, yes.
Okay.
So you cannot change that definition because
Of course not. It has to be completely consistent, right?
Yeah, exactly. So you have a consistency.
So everything is perfectly consistent. That's the miracle. But if you think about it, it's actually quite natural. In fact, I was about to say the other thing, like usual quantum mechanics, why we kind of, like we can kind of still check it quite well and stuff like that. The whole point is the quantum theory doesn't predict only the expectation value for a state, because they get a whole function. Or in our more practical language, people talk about projective measurements, right? When you do a projective measurement, you get a eigenvalue. Of course, the theory cannot predict that particular eigenvalue outcome. What does it predict? It predicts the statistical distribution when you repeat that experiment, right? So in that sense, the theory predicts the whole statistical distribution. So the whole statistical distribution is one way to think about that value as over just the expectation value. The only information is there. Why do you want to throw that away? Right? Only that there is a catch. Of course, you can have the whole distribution for an observable beta and the whole distribution for observable gamma. There is no way for you to construct the distribution for the observable beta gamma out of that. Why? Because the whole distribution doesn't carry the complete value. It loses some phase information. And that's non-complete value catch everything. Well, I think I have to move on a bit faster now. But well, we spend a lot of time here, but in a way it's good because it's showing that you really appreciate what is the key feature here. Okay.
Can I say instead of all these coefficients Zn, which encode all the quantum information of quantum state, you just train them with your Fn infinite number V. Instead of that, use Fn V. Then they keep all the information of quantum state.
Yeah, this is the full information
Yeah.
for the quantum state
and then
on that particular observer.
Yeah, we have infinitely many of them.
Well, if it's an infinite dimensional in Hilbert space, of course, we have infinite many stuff. Yes. If it's a finite dimensional Hilbert space, then it's finite. Or, in fact, now I also have in another paper, I also have an explicit form for some qubit systems, and I even have it for using the Sunday wave function. Then you have expectation error function, and then you have the functional derivative. Of course, you know what a wave function is about. At every point x, the phi x is just a complex number which serves as a coordinate. Only that you have continuous distributed coordinate, and of course you will replace the whole set by a function. In fact, I even explicitly checked there how this definition, this Taylor Porter, everything there actually perfectly explicitly illustrate that you have the Heisenberg communication relation exactly what. And the other thing is one more word I mentioned that before. What if my phi, my state, is a Huygens state of the observable beta? Very interestingly, in that case, all the Wiens are zero. You have essentially a classical value. Make perfect sense, right? Now the rest, well, in fact, this is the most important part, really. This I have mentioned. Again, the emphasis of classical mechanics is really symplectic geometry. The point is, quantum mechanics is the same thing. Well, we have the Heisenberg equation of motion already. I've showed you that with that definition of the quantum Poisson black jet is exact analog of the classical case. In fact, more. Some of you, in fact, may already be familiar with this. Since the 1980s, we know well that quantum dynamics is really Hamiltonian mechanics. You can look at the Sunday equation. Again, we choose a coordinate system, except that now I put it in terms of the real part and imagine by Qn and Sn. There's a real number coordinates that describe the quantum state. You just have to substitute this into the equation here. And we can show the Sunday equation can be expressed in terms of this set of differential equations. What are they? Of course, Hamilton equation of motion. Qn are the configuration variables, Sn are the momentum variables. So that's the con here.
So what is H? H is
H
the
is
definition of H.
H is this. So Sunday equation is really equivalent to this set of equations. Okay. Now again, I can promote this back to this language, right? Now I'm not talking about just the particular time evolution or particular Hamiltonian operator. I can talk about some generic beta sigma here as some H sigma, some generic Hamiltonian function or some operator. And I have an equation like that. Even better, the F here, I don't even write it as a F beta. Because not only the F beta satisfies any function on that symplectic manifold satisfy those equations. Okay? Now,
What is the definition of F beta sigma?
F, well, we have F beta already. So what I mean by F beta sigma is it is the F beta which corresponds to a generic Hamiltonian function with the giving an evolution parameter as sigma.
But the preserved sigma. So sigma is a generalization instead of time.
Sigma is a parameter, yeah. Yeah. So if this beta is the Hamiltonian operator, then the sigma is key. If this beta is the angular momentum operator, the sigma is the theta.
It should be netto charge anyway.
Hmm?
It should be 1 over the netto charge. symmetry generate. It should be one of
Not necessarily.
not necessary.
Because you can have, because the notion of generic Hamiltonian operators is very general, right? I can give a very complicated function of x and p, which may still be a Hamiltonian function. And I can still describe that space. Or you can look at it this way, okay? Because this Hamiltonian evolution, of course, is just what? A unitary transformation on the Hilbert space, right? So I can pick any, I don't need to use the Hamiltonian. I pick any Hermitian operator. I can use it to generate a unitary transformation, a one parameter set of unitary transformation, right? And that parameter, so that Hamiltonian operator is my beta sigma, and that parameter is the same. So any unitary transformation can be interpreted in that form. And that unitary transformation can come from an arbitrary Hermitian operator.
I mean, maybe commit to with the Hamiltonian. Should commit with the Hamiltonian.
Well, essentially, any Hermitian operator goes.
No, that operator should commit to the Hamiltonian.
No, not at all. Not at all. Not at all. This is still a set of equation. It may not have any meaning with connected to
then
physical dynamics.
Then you don't care
It's just my
about time
practice.
evolution.
Hmm?
Then you don't care about time evolution.
Well, time evolution is a special case. So
Yeah, you should care about the time evolution. Hamiltonian is important.
of course, yeah, physically, yes. But I'm saying is all the
At formal level, yeah, you are saying.
the symplectic geometry actually give you all the structure, full set of it, which is the other thing that's also important because that encodes information about symmetry.
Yeah, there are some symmetries that are more important than others.
Exactly, of course, absolutely. Okay, yeah. So the next thing is, now we see that zoom the picture actually can be extended to think about as something like this. Heisenberg equation of motion, likewise, can be extended to think about as something like that. Of course, we have a specific case for sigma being time t, but now the thing is, I already showed you, each beta corresponds to f beta. And then the Taylor product tell you how to connect operator product to this non-commutative product between the f's. Now everything here match exactly to that. Everything here match exactly to that. I mean, this Poisson bracket is some function on the phase space. It corresponds to some operator that is exactly this operator. Perfect one-one matching. To the extent I'm actually claiming this two equation is exactly the same equation described in two different sets of coordinates. This is in terms of the complex number coordinates, or if you express it in terms of QNSN, the real number coordinates, and you may have infinite number of them. This is in terms of what? The non-coordinate, the position operator, momentum operator, as exact coordinates. We have equations like that with a proper definition of the operator derivative, which is just given here. In fact, this set of equations, we're basically what we're exploiting. We are exploiting the Hamiltonian vector fields to define the coordinate derivative. This set of equations, if you just remove the hat and replace this thing by the corresponding expression of the Poisson bracket, you have the classical, exact classical analog. It's again just symplectic structure. Okay? So, and I actually, in a particular paper, I actually have described this whole thing about transition between screen picture and Heisenberg picture in this more general language than time evolution as a coordinate transformation. between the infinite number real number coordinates or complex number coordinates and the 6 non-commutative coordinates. 6 non-commutative coordinates can carry the same amount of information of the infinite number of real number or complex number coordinates because of what? Because each value of each non-commutative coordinate is this non-commutative value which have the information of infinite number of real numbers, right? So everything is consistent and can be pieced together, and you can extend this. This is essentially just replacing the transformation between Heisenberg picture and Schooling picture, replacing the ddt there by just the d. And you can use it to define whole differential calculus for the non-commutative geometry in the non-commutative language. And the result you get out of it, I got out of it, is completely consistent with the general definition of differential calculus for non-commutative geometry as given by the mathematicians. But here, in a way that you can that you can easily appreciate just from quantum mechanics. Okay.
How much time do you need to work?
How much more time I have? That's the question. I can, yeah. How much more time I can have? I can log it up right now.
15 minutes.
Okay. I'm sorry. Okay. Yeah. Yeah. Okay. This is to answer one question. I start my first page talking about non-commutative geometric picture of the physical space, right? But all I talk about here is space-time. So how can I get back that physical space? Well, I think the answer is here. Because remember that Qn, Sn, I dropped the two factor here. So Qn, Sn as the configuration variable and momentum variables are just the real part and imaginary part of that complex coordinate. But if I transform it by a phase, of course, everything still works perfectly. So, of course, that phase transformation is a very, you can say, a very fundamental symmetry of the quantum system, which means what? You multiply by a phase, you change the real part and imaginary part, right? You mix the real part and imaginary part. So, in fact, I have a symmetry theoretical formulation. The symmetry I talk about here is simple, except based in a little bit unfamiliar ways. It is just the Galilean symmetry with the time evolution dropout. Okay? And if you don't care about speed, then you don't worry about the rotational part, then it's just essentially Heisenberg symmetry. Except that you have to put it this way, and that's the only proper way to put it. Because the position operator cannot correspond directly to a generator in the V algebra. Otherwise, you see, momentum is additive, mass is additive, position is not additive. But if we follow the group theoretical construction, an observable for a composite system would always be additive. I mean, not an observable, a representation of an element of the V algebra for a composite system as the product of representation of the irreducible parts for the elementary system would always be additive. This is the only way to avoid it. In fact, it's a good way, because if you look at Heisenberg symmetry, the mathematician will tell you all the irreducible representation correspond to what? You have descent pretty much one parameter set correspond to a high value of this guy M. In fact, M is a cosmetic invariant. It's linear, but it commutes with everything, right? And what is it? That's actually, of course, the Newtonian mass. So in a quantum symmetry, you actually have Newtonian mass as the only Well, other than speed, the only characteristic that represent any system as an irreducible representation of the quantum symmetry. Of course, whatever mass the particle has, you still have that essentially the same Hilbert space picture, the same phase space. What you don't have is anything like just a configuration space. Because of the fundamental symmetry that bind the two parts together. In fact, this is easy to understand. You think about Lorentz symmetry. Minkowski spacetime is an irreducible representation of the Lorentz symmetry. You cannot separate the space part and the time part, right? Because the choice of space and time direction is just reference frame dependent. The whole thing is one representation. When you go to a Newtonian limit, you break down the two parts as independent representation. So we have a parallel story here. At the quantum level, the configuration space and the momentum space do not have independent meaning. You have one thing together, the phase space. We go to the classical limit, you can split it in two parts. At the quantum level, no. Therefore, the quantum phase space is the quantum physical space. And we have a non-commutative description part. And this is even, I would also love to mention this thing. The wild algebra, what is it? It's just, you can think about the polynomial algebra of X and P for your Heisenberg computational relation. Okay? Now, of course, we're interested in having three pairs of it. Then, if you restrict to this algebra and look at the Hilbert space as a module where this algebra acts on, then there is actually an algebraic notion of dimension defined for this object called the Gelfand-Chauvillov dimension. And the answer is 3. Or it's 7. It depends. This number is n if you have n xp pair. Okay? So this quantum picture of the physical space as the phase space even agree with our very intuitive notion that physical space is 3-dimensional. Except it's not real number dimension, it's just Gelfand-Chauvillov dimension of some non-commutative module of some non-commutative algebra. Now I think I should really rush by and skip some of the other thing. Well, let me look at here. A similar picture of this I showed in 2009. That was my starting point, informed special relativity. The thing is, this is quantum mechanics here, right? That's the theoretical representation. You can go to classical limit as one on top of SH value zero limit, which is not exactly that actually. And this is what the Lorentz covariant version. You promote the free index to 0, 1, 2, 3, inclusive for indices. Okay, so this is relativistic, if you like. This is non-relativistic. Quantum at this level. Down here, classical. We have constructed this theory, which is actually very different from the usual relativistic quantum mechanics, that actually and show that and show every notion work well there. And we use this so-called symmetry contraction to take the symmetry to its various approximations. The same contraction can apply to the dynamical theory as a representation of it, which we treat the dynamical theory at a lower level. So this part is completely worked out. And everything is perfect and fine. Deformation is essentially the inverse of contraction. So contraction is, if you like, as like this is going to C to infinity limit. You contract the Lorentz symmetry to the Galilean. Going backward is so-called deformation. And what deformation or contraction option you have is actually completely fixed by the algebra cohomology, some topological issue. So it's not quite arbitrary at all. Its options are quite limited. And something like a stable symmetry, stable Lie algebra Lie group. Yeah. It's called stable because you cannot deform. It doesn't, there doesn't exist any deformation. That is to say, that symmetry cannot be an approximation of some symmetry. Okay? But otherwise, so long as it's not simple, it can be placed as an approximation of some symmetry, and then you can go back up. So my starting work on deformed spectral activity is to look at a symmetry picture and going bottom up. And then the contraction is the top-down picture, because you cannot rely on the deformation to give you the dynamic. That would be very difficult. You want to construct the dynamic of some representation theory at upper level and use this structure. Of course, you use the contraction structure to guide you, so that whatever theory you construct at the upper level guaranteed to give you the correct theory at the lower level. So constructing the theory about, well, I still haven't started working on that. But this theory already is quite interesting. Let's move on here. As I said, I have a relativistic quantum mechanics picture, Lorentz covariant quantum mechanics picture, which is different from what other people have. The key difference is, but first of all, it's truly consistent. Their theory are not consistent. Actually. The integral definition, the inner product definition, wave function, square integrable thing, those are total bullshit. Because they diverge. You can't get a converging integral. Like mine never have that problem. And you can even look at it as the Moyer star product kind of thing, because that is exactly just the deformation from the classical observable algebra to the quantum observable algebra, the Moyer product deformation. It's just the consequence of the deformation on the universal enveloping algebra as a consequence of the basic deformation on the Lie algebra. That kind of deformation contraction I have been working on. And everything comes out of it naturally. Now what I have in this theory is my integral, as I say, my inner product is different from that. How is it different? Yes. This is the inner product. Now what is this eta hat here? In fact, Pauli, Dirac and Pauli worked on something like this a little bit years ago. Nowadays, we call it pseudo-Hermitian quantum mechanics. Okay, so and Pauli called this a metric operator. They didn't go very far. Part of the reason I think is they're working with notions like that without even distinguishing the upper index and the lower index for Minkowski effect, the covariant and contravariant indices. They don't even have that notion there. But actually, one can phase our line, this model of our in that line. So this is, for example, what this metric operator do to the position operators. Okay, so it is exactly a representation of the Minkowski metric on the vector space of state, which is now not a Hilbert space because the inner product is not positive definite. The metric operator defines the inner product. And this inner product has to be, well, it's just like Minkowski space-time. You don't have a positive definite inner product. You have time-like vector, space-like vector, light-like vector. This is an exact quantum analog. And I need this because otherwise, remember, I want my position operator, momentum operator to be what? To be coordinate or non-commutative coordinate of that non-commutative geometric picture of the quantum physical space, right? I need a Minkowski analog. And I have it as a much better behaved Lorentz covariant quantum thing. So I'm essentially done here. This is the last page. What next? I mentioned this already. If we want to go further up, what is this level? If we correspond to something where you have x not commute, pp not commute. Okay. In fact, I actually believe the quantum phase space as a non-commutative geometry is like the Euclidean geometry for non-commutative geometry. Well, it hasn't. If we get back to this picture here, the Hilbert space has a metric operator to it, only that is trivial. The identity operator is the metric operator for verified quantum mechanics, of course, because it's Euclidean, and this is inclusive. So now it could be more interesting when we have XX non-commute, PP non-commute, which correspond more to what other people talk about in non-commutative geometry, except my emphasis would be you will only want to look at phase space. Non-commutative geometry of something like configuration space only, that's completely meaningless. You have to focus on phase space. Okay. Now, I have Lorentz covariant quantum mechanics. How about quantum field theory? I'm working on that. I'm starting to work on that. How about gravity? Well, I'm also starting to think about it. Okay, this is a metric operator. What if we have a metric operator which is not trivial, right? Would that be a way to get quantum gravity? That would be extremely interesting. Quantum information, I mentioned it already. In fact, well, I kind of flip over that page. I like it very much. Again, the philosopher Creed has this very interesting statement. We call real numbers the convenient fiction. Well, as like a mathematician say, real number doesn't exist in nature. Real numbers are abstract symbols we create to represent some conceptual notion.
Everything should be true for any true number, any mathematical invention.
Exactly. Any mathematical notion is an abstract notion, as an abstract notion is not reality. Okay? And abstract notions are not intuitive. That's what you mean by it being abstract. But they can generally be compatible with intuitive notions. So there is nothing intuitive about real number as value, and nothing counterintuitive about my non-commutative value. Real numbers is just a model we use to describe value of physical quantity, which works well so long as classical physics is concerned. Therefore, it is the convenient fiction. When quantum mechanics is no longer convenient. That's why my non-commutative value is the new convenient fiction. Now, but Bohr keeps telling us one thing, right? Bohr keeps telling us that measurement of any quantity can only give you real number. Is it right? You forget about one thing. The real number we read out of an experimental apparatus. What I said already. Real number doesn't exist in nature. How can we read a real number out of the apparatus? Because we calibrate the outputs down with real numbers, right? The real numbers we're reading are the real numbers we put in our calibration process. But then it just maybe if somebody finds some smart way to calibrate our experimental equipment with non-commutative numbers, Q numbers, we can measure non-commutative value directly. It sounds more like fantasy at this point.
So at the end of the day, what is the measurement that you compare with these two numbers?
Well, I would think any quantum information process is essentially some sort of measurement process. What is a measurement?
Sometimes it's an infinite, if it's in an infinite sequence, you cannot measure anything.
No. First of all, even if it's an infinite sequence, for example, how about measuring the expectation value function? We're not unfamiliar with measuring functions. A function is in the number of values, right? Of course, you do approximation. So in principle, infinite number of values is measurable. It's not unmeasurable, it is measurable. And in my paper, I also show explicitly how every single element on that infinite sequence is in principle experiment can be determined through experiment. Okay? But whether there's any way to kind of extract that, to directly deal with quantum information as quantum information. I think that's what it's about. To deal with quantum information directly as quantum information and find some new, use some new symbols, new ways, new mathematical tools to deal with that quantum information. Then maybe there's an all particular assessment. I don't know how to do it. I have no experimental talent at all, but it is possible. Finally,
what about usual energy spectrum, hydrogen atom energy spectrum? How the energy values will be extended?
You mean the eigenvalue?
Yeah.
I said it already, because when you have a Hagen-State, the value of a Hagen-State, the value of an observable for this Hagen-State will have all the V being 0. So essentially, you just have the eigenvalue.
So can you have some prediction which ordinary quantum mechanics doesn't give you, but still prediction for any experiment?
So long as non-related quantum mechanics is concerned. This is just a description of the existing theory. I don't change the theory at all. I only extract or give the non-commutative picture of looking at it. But that picture tells you what? Every physical quantity has a fixed value, the non-commutative value. And everything about quantum mechanics is not that different from classical mechanics. It's just a non-commutative version of classical mechanics. In fact, I even write a paper, I even published a paper in this journal called Studying in History and Philosophy of Science, with the title Non-Commutative Quantum Reality. Quantum physics is as real as classical physics, except that everything is non-commutative. You think about it in terms of non-commutative value, no problem. So, but yeah, new prediction, really new prediction, no, I don't have. For with quantum mechanics. But based on that framework, I have a non-heuristic theory. But based on that framework, I have a heuristic theory constructed, which is completely different from what is available now. So there should be guaranteed to be, in a sense, new predictions. But I can't tell you any of such prediction right at this point because I haven't worked it out. I have only worked on the formulation up to this point. But more importantly, this gives you a framework. You see, we are all, as theorists, we are always interested in finding a different way, a new way to look at an old theory. Why? Because the old way of looking at it may only work for that theory, while the new way of looking at it may actually allow us to look at a deep level theory, right? How do we generalize? How do we get from what we know to what we don't know? We have to look at what we know in the right way. Then maybe you can move on. So the whole framework provides a channel to go way beyond that. And I would claim it even provide a possibility of going beyond the existing mathematics. Because so far, we still talk about algebra. And real numbers still play a specific role here because algebra is a vector space. Every algebra is a vector space. The scalars are what? The real numbers. What if we replace those scalars by the non-commutative number? We have a new kind of algebraic structure. We can still call the algebraic structure. And in fact, when I was thinking about the tangent space of that non-commutative space, it seems to be asking for a notion like that to have things work out. After all, there is this, I don't know how to explain it. In non-commutative geometry, non-commutative algebraic geometry, you have a notion of complete factorization, root of polynomial set, okay? Work out completely within the algebra. What do you need? Of course, you need the real number values, and the real number values are elements of that algebra, right? They're scalars, but they're also elements of that algebra in the sense that you have a unit as one of the base, an abstract unit as one of the base vectors. Now, if you want to do the analog for non-commutative algebra, you will need my non-commutative value. Then you have to go beyond the usual algebra thing. Well, I would certainly love to talk to some mathematician about what you can do in that direction. So I'm done here. Thank you. I've been much overrunning.
Okay, let's go for interesting talk.
Thank you very much.
Questions or comments?
I have one question or comment. Can you hear me?
Yes, yes.
Yes. So maybe I think you are considering deformation, I mean the non-commutativity between time and space as well.
Yeah, yes.
Right. Then, so in the user, I mean, in the string community, I mean, treating the non-commutative geometry, that kind of thing, I mean, was first proposed, but later withdrawn because of the causality problem. What do you think about that? So I think, I mean, if you consider...
That, of course, is a very interesting question, but it's also a very tricky question to think about. I mean, here, essentially, I have a theory which would have some non-commutative value for time. Now, how to understand causality when time is some non-commutative value? I don't know how to answer that at this point. I don't know how to answer that at this point. But one thing I can say is we don't know how to think about it.
Oh, I see. Okay.
So we don't know how to think about it yet. But of course, we should try to work it out. But before we go into that kind of level, it's premature to say anything about it.
Okay,
but of course, there are also people who question whether one needs to have causality at the very basic level of the theory. That's something else.
Okay, thank you.
More questions or comments? Okay, then I'd like one question. You have introduced Taylor product.
I don't introduce Taylor product.
Yeah.
Italian gentleman introduced.
Yeah. So,
I applied it to the value note. I think the value notion.
That seems to me that the representation of the algebra on the Hilbert space is unique. I think that's okay in quantum mechanics, but as is well known, quantum physics during curved space-time, we need inequivalent representation of a Hilbert space from the unique algebra. So I'm wondering how that fact can be realized.
Can you say that again? I don't exactly.
I think the Hilbert space representation of the algebra is not unique in general. Yeah, but in your case, the representation seems to be unique, given by the Taylor product, right?
No, not really, not at all. You can choose a different base to work with, and the coordinates of
No, I'm asking the different Hilbert space representation. Changing the Hilbert space itself.
You mean you come straight to a completely different Hilbert space?
Yeah. That is known mathematical fact.
But then there's a from the symmetry theoretical formulation point of view, you're talking about different representation. Yeah. And in principle, it's a different theory.
A different representation of the algebra on a Hilbert space.
Different representation of the algebra on the Hilbert space. Yes. I understand. Yeah. I understand. But I'm saying the way I try to look at it is I start with Lie algebra, Lie group, okay, and then look at its irreducible representation as giving me the field. Now, the observable algebra would come from something like the universal enveloping algebra or the group C star algebra or some extension of it. So once you define the representation of the Lie algebra, you fix the representation of all of that.
Yeah, so you mean that you have already fixed that?
Yeah. I mean, of course, the Lie algebra can have a good number of irreducible representation, but in the Heisenberg case, that just correspond to particle given mass.
Okay, thank you.
But there is another very interesting way to look at that too, because I have this contraction scheme, right? I have this contraction scheme. And of course, you all know, you start with some symmetry, look at a certain irreducible representation of it. Now, if you do a contraction to an approximate symmetry, that representation, irreducible representation at the upper level, may become actually a sum of irreducible components at the lower level. Then, independent irreducible representation at the lower level may actually come from one single irreducible representation at the upper level.
Okay, if there is no more question and there is no question from the online, let's thank speaker again.